Hello and welcome to this clip on how to deal with more challenging Hess's law questions. Or perhaps I should be more honest and say Hess's law questions that look a little bit different to maybe the ones you're used to or the ones you might have looked at in the textbook. If you think about the types I might be discussing here, we're talking about when you get the enthalpy of reaction given to you instead of having to work it out using a set of data. So in a nutshell, what will happen is, because you already have the answer to it, so to speak, there'll be a part of the process, a part of the calculation that you'd normally have that's actually missing. For example, an individual bond enthalpy for a certain bond, or a specific enthalpy of formation or combustion of one particular substance that's in the indirect route. So all you have to do to deal with this type of calculation is to make the subject of your expression, so your individual bond enthalpy, for example, the actual subject of your calculation that you do. So eventually what you're looking at is you're turning it into x and making x the subject of an expression. You'll have all the other things you need, it's just a bit of rearranging. Let's look at an example. So let's look at this one. It's a section of a bigger question. I've taken the sort of difficult sections of larger questions and tried to sort of delve into them a little bit and trying to deconstruct them to make them a bit more accessible. So if we look closely at what this one's asking us to do, they actually want us to calculate the standard enthalpy of combustion of gaseous methanol. Now if we look at both of our candidates, both of our stage 1 and our stage 2, methanol is not present in either of them. So therefore it must mean that they are part of a Hess's law cycle. So the first thing to do is to draw out the equation that represents the enthalpy of combustion of gaseous methanol. So this is my combustion of gaseous methanol. It's the standard enthalpy of combustion because everything is in its standard state. And it's also 1 mole of methanol. Now it also gives us some other information. It tells us the standard enthalpies of combustion of carbon monoxide and of hydrogen are minus 283 kilojoules per mole and minus 286 kilojoules per mole respectively. So we can make use of this as well. Perhaps the most useful clue to disentangle this question is to what it actually tells us to do. It says use these data and the enthalpy stage is the enthalpy change for stage 2. So that means we don't actually have to worry about stage 1. They've put stage 1 in there as a decoy. It looks like it might be part of this, but if you think about what the question is telling you to do, it even gives you a method. Use these data and the enthalpy change for stage 2 to calculate a value for the standard enthalpy of combustion of gaseous methanol. So at the bottom, what I've put, instead of specific elements in their standard states or specific combustion products in their standard states, as you'd usually do for enthalpy of formation or for enthalpy of combustion respectively, this time I've put in the values that they've told me to. So I start by putting in my hydrogens, my H2s, and there's 2 of them, so it's 2 lots of minus 286. And then I add my carbon monoxide, which is minus 283. So I total them up and that gives me minus 855 kilojoules per mole. Now, going from 2H2 and CO up to CH3OH, that also gives me stage 2. If you look closely at it, it's actually the reaction I've got to label. So this one. So going upwards, that would be minus 91 kilojoules per mole. But obviously, my direct route is going to take me the other way. In other words, I'm going this way. So if I move the page down, I'll show you how I can pull it all together to get the enthalpy that they want. So just like normal, working my way around from left to right, reversing the sign of the minus 91 because I'm going in the opposite direction to the arrow pointing upwards there. It gives me minus 764 kilojoules per mole to the minus 1. So if we go on and have a look at another one now. So this one is different because you have to make the carbon-hydrogen bond enthalpy in ethane the subject of your expression. So in other words, it's one of these. So one of those particular bonds has to be the subject of the expression. And this is the only problem. You're used to doing bond enthalpy calculations like that, with delta RH being the unknown and the bond enthalpy of reactants and bond enthalpy of products all being provided for you. However, this time they've given you delta RH. In other words, it's minus 136. So what do? So the first thing to do is to add up all the bond enthalpies of the reactants, because if you look closely, the reactants actually are given. We have carbon double bond carbon, we have H single bond H, but we don't, interestingly, I take that back from a couple of seconds ago, we don't have C single bond H. So it leaves us having to apply an algebraic expression, making X our carbon-hydrogen bond. So you can see there's 4 carbon-hydrogen bonds on the left-hand side. You have 1 carbon double bond carbon, which is 612, and you have 1 hydrogen single bond hydrogen, which is 436. So that's the bond enthalpy of our reactants. Now we can take away the bond enthalpy of our products. And seeing as we've got 6 carbon-hydrogen bonds in our ethane, that means 6x. So we've got to collect like terms for x, so bring those two expressions for x together. So subtracting one from the other, that gives us 612 plus 436 minus 348 minus 2x. So now we've got to try and work out what 2x would be. So that gives us 2x is 836, because I brought the 136 over and added it to the other side, and that gave me, dividing by 2, 418 kilojoules per mole to the minus 1. So let's now do a couple more. So here's one where we have to calculate a value for the standard enthalpy of formation for gaseous hydrogen cyanide. So you're given a reaction in the actual question, HCN plus 2 1/4 O2, giving you half H2O plus CO2 plus NO2, and you're given a collection of data. Normally when you do a Hess cycle, in most questions they ask you to actually work out delta RH. So in other words, what would be the delta RH value for that particular reaction? So let's draw it out and see what we can do with what we've got. So now what we've got to do is look very, very carefully at what kind of data that we've got. We've got standard enthalpies of combustion. Now the normal thing we do with enthalpies of combustion is a Hess cycle that looks like this. So that little red version up in the top left-hand corner is what a normal Hess cycle using combustion enthalpies might look like. You'd have your reactants going to your products, you'd be trying to work out what the overall reaction would be, the delta RH value, and you'd have combustion data that you can point downwards at the combustion products, such as CO2 or H2 or whatever. Here, we don't have the reactants and products that we need to draw that kind of Hess cycle. So why do I say that? Well, we have H2O, we have CO2, we have NO2. So what's going on? Well, they must be the combustion products themselves. So what do I mean by this? Let's just highlight it for a second. These here, they're all oxides, aren't they? So they're going to be the products of combustion of hydrogen, of carbon, and of nitrogen, respectively. So how do we sort of square that circle in the case of this particular Hess cycle? Well, the key lies in what we're actually being asked to do. We're actually being asked to work out the value for the standard enthalpy of formation for gaseous hydrogen cyanide. In other words, this one up on the left. So our unknown is on the left-hand side. So let's have a look at what we've got. We've got hydrogen, nitrogen and oxygen in our box at the bottom. Well, lo and behold, if we look at our data, we've got the combustion enthalpy for hydrogen. So let's put it in. We've got it right there. We've also got carbon and nitrogen, similarly. So the next trick is to realise that we've actually got the reaction going across the top as well. So going across the top, you've actually got the combustion of HCN. So I've ticked them off because we've got them all in that table, haven't we? Now we've got to think really carefully is where do we start? Well, it's asking us for the standard enthalpy of formation of gaseous hydrogen cyanide, which is this one over here. That's the direct route. Our indirect route goes from here all the way across, doesn't it, to end up at HCN. So what we do is a slightly different indirect route. We start by adding up all our delta CH's, and that should take us to HCN. So let's try that out. So we've got our hydrogen, half delta CH of hydrogen. Double tick that. And we've got the combustion of carbon as well. I've just realised I made a little mistake. I'm just going to rub it out. When I labelled the delta CH for CO2, I should have actually just put delta CH for carbon like so. I'm just rubbing it out there. There you go. Apologies for that slight mishap earlier. So carrying on, we've now got that one sorted. The third one is half times delta CH for N2. So just to double check, we're now up to the right hand side here. We've dealt with all of these. So now we're heading over this way. So to head over that way, we're going in the opposite direction to reading left to right. So if we look at what that value would be, that would be minus 611. So that means we have to say plus 611. And now we can work out the delta FH value. So that gives us positive 130 kilojoules per mole to the minus 1. We've got one more to do, but this one's a little bit easier. That's probably quite a hard one, hence why it's 4 marks instead of the usual 2 or 3. So let's move the screen down so you can see the last one to look at. So this is one more 4 marker. So it says a vessel and its contents of total heat capacity 120 joules per Kelvin to the minus 1 were heated using a methane burner. Notice it doesn't give you grams to the minus 1. It doesn't say what the mass of the vessel is. It doesn't mention mass of water. So you're not using the standard heat capacity of water this time. You're provided with an alternative value that you haven't seen. So all you do is just plug that in as if it was normal. So we're at a crossroads here. The mass times the specific heat capacity is 120 joules per Kelvin. It must include the mass because it doesn't mention grams there. So now what you've got to do is work backwards from 0.10 grams of methane. So remember there's the second step in this whole process as well, isn't there? Which is how to actually get the enthalpy of combustion. So what we can now do is start substituting in some values and working backwards. So if we apply moles equals mass over mR for methane, that gives us that denominator. And we already know that we're given in the question that minus 890 kilojoules per mole is the enthalpy of combustion. So now what we've got to do is work out what Q would be in kilojoules. So that gives us minus 5.56 kilojoules. So remembering that Q is simply neither plus nor minus at this particular point, we just change that into 5560 joules. Instead of Q. We know that MC is 120, so now we have an expression we can work out, which gives us 46.3 Kelvin. So hopefully these 4 examples have shown you the different ways in which they might approach questions that you might see in an examination. You would be unlikely to see more than one question like this in one examination, but with any luck it's given you some ideas about how to go about approaching the calculation so that it doesn't just cause you to come up short. Always try and look for a way to rearrange the equation. That's all they really are trying to get you to do. Okay, so it leaves me to wish you good luck. You can go and try some examples now and come to one of us at college, or perhaps come to a subject extension to try and suss it out. But do have a go at a couple before you do so, because it'll make you better at doing the harder style enthalpy questions that you're likely to come across. So for now, thank you very much for listening, and see you soon.